Hello, everybody. We are case study group 8, and so just to jump right into it. So our particular case study is centered around this particular paper, which is titled Introduction to Machine Learning, Neural Networks, and Deep Learning. This particular paper is actually kind of centered around these topics and their applications to the medical field in particular, but its overall purpose is to explain these topics in kind of non-technical layman's terms. So it does a pretty good job of that. So we'll see some examples in the medical field, like applications in the medical field, but overall general explanation. So the topics that it covers and that we'll be further presenting in this presentation will be the things like types of machine learning that exist, the actual classic machine learning models, some neural networks, even convolutional neural networks, and even some machine learning and deep learning applications in ophthalmology in particular. And so this particular slide is just to kind of provide some clarity on some of these highly associated terms, particularly being artificial intelligence, machine learning, and deep learning. But just the figure on the right there is pretty much the best summary of all this information, being that machine learning and deep learning are just pretty much specific methods of artificial intelligence, being the field of automating intellectual tasks that are normally done by humans. But in any case, that figure is the best summary of that. I'm going to use that to transition into the different types of machine learning that exist. And so including supervised, unsupervised, semi-supervised, and reinforcement learning. As far as our particular class is concerned, we're already pretty well familiar with supervised and unsupervised learning, but just to quickly review here a little bit. So supervised learning in particular being focused and reliant upon the labeled data in its training phase. So in other words, having access to those features and targets, which can also be thought of as like having access to both the questions and the answers and learning from that. So kind of like a cheat sheet. Whereas unsupervised being having not access to those answers, the cheat sheet. So the model is left to, or algorithm is left for itself to find any patterns that may or may not exist within the data. And then these last two are probably the lesser known ones, and thus maybe a little bit more interesting, starting with semi-supervised, which is probably the most self-explanatory out of them, being the combination between supervised and unsupervised learning, meaning that it can deal with both labeled and unlabeled data within its training phase. In its process. And then this last one, reinforcement learning, is actually the most unique and kind of interesting one out of all of them, particularly being that maybe the first thing to mention is that it doesn't actually, unlike these first three, doesn't actually learn or train through data in particular, but rather through trial and error. And this is because what's normally asked of a reinforcement algorithm is to accomplish an overall desired task or outcome that doesn't necessarily have one single correct answer. So the example provided by the paper, for instance, was asking a reinforcement model to complete a game level in a Super Mario Brothers game. So we're not, in that case, we're not looking for a specific sequence of inputs to say accomplish that said task, but just to make sure a model that can get to that point. But in any case, also reinforcement learning is not, there's not as many applications in the medical field according to this particular paper, so it doesn't get brought up that much again throughout the rest of the paper, but it was still nice that they brought it up. But in any case, that kind of wraps up the general introduction section of this presentation, so we can move on to the next one.
Okay, from these slides, we'll be discussing about classic machine learning methods that are commonly used in medicine. These methods have been widely used in various applications and have proven to be effective in many scenarios. So we can see here linear regression, logistic regression, and decision trees and random forest. So let's go through each of these methods. Can you go to the next slide? Next slide, please. Okay. Linear regression. This is one of the simplest machine learning algorithms. It is used to find relationship between one or more numeric features and a single numeric target. Um, for example, it uses a straight line to describe the data. Here in this linear regression, we use a slope intercept form, or in univariate linear regression. You can see here y is equal to ax plus b. The slope a represents how much the line increases on the y-axis for each increase in x, and the intercept b represents a point where the line intercepts the y-axis. So in the same way, in the multivariate linear regression, multiple weights for different features influence the target. We measure these model errors using residuals, which are the vertical distances between predicted and actual values. And the goal of the linear regression is to minimize the errors using an iterative optimization algorithm called gradient descent. Next slide, please. And the next one we're gonna discuss is all about decision trees and random forest. We commonly use decision tree, which are used for both classification and regression tasks, as well as the decision tree. We know that the decision tree starts with a root node and make decision based on features to split the data into different classes or groups. The process of recursive partitioning continues until the terminal nodes are reached. You can see in the figure, which provides the final class. Random forest, on the other hand, is an extension of decision tree and are known as ensemble methods. They uses multiple decision tree, each created using a subsample of features to predict the final class based on the majority voted among all the trees. Next slide, please. So the final one we're going to discuss is all about logistic regression, which is a classification algorithm. It estimates the probability of a particular outcome based on the input features. Unlike linear regression, which uses a straight line, logistic regression uses a sigmoid curve to estimate class probabilities. The sigmoid function produces an S-shaped curve. You can see in the figure. That converts input features into probabilities between 0 and 1. This method is advantageous because it ensures that probabilities are bounded and cannot be negative or greater than 1. Logistic regression can be binomial, where there are only 2 possible outcomes, or multinomial, where there can be 3 or more possible outcomes.
So in this logistic regression with a threshold value of 0.5, we can see that the above 4 points are classified as yes and the below 4 points are classified to be no. Suppose if we reduce the value of threshold to somewhere around 0.2, then these two in between points will also be classified as yes, which wasn't the case in the previous instance. So now you are having two different models with two different threshold values. So no matter which model you use, you always want an evaluation metric to decide upon which model is performing better. And in this case of classification, we are going to have confusion matrix. Next slide, please. So confusion matrix is nothing but comparing the true labels in our test data with those predicted labels by our ML model. So here true positives and true negatives are nothing but those labels which have been predicted correctly. And there are also false positives and false negatives. False positives means those labels which are falsely predicted to be positives when in fact they were negative. So same is the case with false negatives as well. Suppose if you are having two different models, then you will have two different confusion matrices. And it's easier to compare those two matrices and say which model is performing better by seeing which confusion matrix we have most things which are being correctly classified. Suppose if I want to test the logistic regression with 10 different threshold values, then I'll be having 10 different models, which leads to 10 different confusion matrices. So it is far difficult to analyze all these 10 confusion matrices at once. So this is where the concept of ROC curve comes in. So to calculate the ROC curve, we need two values, which is nothing but true positive rate and then false positive rate. True positive rate is nothing but of all those positive labels, how many of them are we correctly predicting to be positive? And so we want the value of true positive rate to be high. And coming to the false positive rate, of all those negative labels, how many of them are we misclassifying to be positive? So which means we want the value of false positive rate to be lesser. So next slide, please. So now suppose if we are doing logistic regression with 10 different threshold values, then we'll have 10 different confusion matrix. So for each of them, we can calculate the values of true positive rate and false positive rate. And then keeping all of those values on a graph, this is how the graph looks like. And this is called the ROC curve. So as we just discussed, we want the value of true positive rate to be high and the false positive rate to be low. So there are two highlighted points here. So these two points are the case in which the value of true positive rate is almost close to 1, and then the value of false positive rate is close to 0. So, and then if we want to decide upon which of these 2 points is best, then you need to bring in the concept or what you are trying to analyze on. Suppose if you are dealing with COVID, then you want all those positive cases to be detected. So to select which of these points is the best, you always get this concept of how many false positives you are willing to accept. Yeah, next.
Okay, so let's move on to the topic of neural networks. Neural networks are inspired by the biological neural network that works in our body with the help of neurons. Just like neurons pass information from one cell body to the other using axons and dendrites, the synapses between the cell bodies are strengthened by correlated outputs. So to follow the same nature, we weigh the nodes in a neural network depending on the ability to give the desired outcome. And perceptron is the simplest machine learning algorithm followed in a neural network. So if we consider the diagram you can see on the right bottom side, it represents a perceptron that is taken in 3 features, performing some process on it, say for example a sigmoid function, and then giving an output within a range of 0 to 1. So the perceptron is basically finding a line, plane, or hyperplane that is able to classify the data into some class. Now, when I say this, some of you might get confused with neural networks and logistic regression, but logistic regression gives the output as the probability, like Santosh mentioned. However, in neural networks, we're getting class association as the output. Next slide, please. So in an artificial neural network, which is based on a perceptron, we can see multiple layers of a perceptron. If you look at the right top image, you can see there are multiple layers, the yellow, blue, and red layers. The yellow layer here will be the input layer, which is taking the features from the data set. The second layer is basically a hidden layer that would perform more functions on the input from the previous layer. And then the last layer is basically the output layer. And this is just an example of a simple artificial neural network, whereas deep neural networks can have tens or hundreds of layers. So they can be very complicated and have many hidden layers between the input and output layers. Now, the perceptron had the sigmoid function in the previous slide. But in case of artificial neural networks, a variety of functions can be applied. Like on the right bottom side, you can see sigmoid, hyperbolic tangent, and identity and rectified linear unit functions. These apply different functions on the data and convert it into different ranges. Like the sigmoid function converts the values to the range between 0 to 1. Hyperbolic converts it from -1 to 1. Identity converts it to the same -infinity to infinity range, and rectified linear unit converts it from something between 0 to infinity. Now, Feed-forward neural networks is when the information from one layer is forwarded to the next layer and so on. It's the flow is unidirectional. Whereas in recurrent neural networks, if the information from one layer is forwarded to any node in the same layer or in the previous layer, then that is called as recurrent neural network. Next slide, please.
Yep. So convolutional neural networks are deep learning algorithms designed for image processing tasks. They extract features from an image by processing it through convolutional and pooling layers, which allows them to identify complex patterns and objects within the image while preserving its spatial context. This makes them particularly effective, such as image classification, object detection, and segmentation. Compared to artificial neural networks, CNNs have several advantages for image processing tasks. ANNs process input data in fully connected manner, which can be computationally expensive and can lead to overfitting when working with high-dimensional inputs such as images. So CNNs, in contrast, CNNs can use shared weights in convolutional layers, reducing the number of parameters and enabling them to process large image data sets more efficiently. Moreover, CNNs can learn hierarchical features, with lower features being detected in earlier layers and more complex features in the later layers, which makes them particularly effective for complex image recognition tasks. So here is a basic CNN architecture, and we have the input layer, the hidden layers, and the output layer. We can have many hidden layers, but I'll explain few of the important ones. So the input layer to the CNN is an image or set of images presented as a numerical value, typically between 0 and 255 for grayscale images, and between 0 and 1 for color images. So coming to the convolutional layer, it consists of a set of filters and kernels, each of which extracts a specific feature from input image. The filter is small matrix of weights that is applied to the image in a sliding window fashion. The output of the convolutional layer is the set of feature maps, where each feature map represents a specific feature that the filter has extracted from the image. And filters in CNNs are trained to extract specific features from images, such as vertical lines or U-shaped objects, and mark their location on the feature map. So the next layer is the activation function. So the output of convolutional layer is passed through an activation function, such as ReLU or tanh, which adds a nonlinearity to the output. So the other layer is the pooling layer. The output of activation function is then passed through a pooling layer, which downsamples feature maps by selecting the most important information from each feature map. So the most common pooling algorithm is max pooling operation, which selects the maximum value from each pool. Next slide, please. So finally, we have the output layer, which takes the pooling output as an input and produces the final output. So which can be a class label for classification task or a set of values for the regression task. So basically, the CNN is trained using backpropagation, which computes the gradients or loss functions with respect to the weights of the filters and updates the weights using an optimization algorithm. During the training, the CNN learns to extract most important features from the input images and maps them to the correct output class. So this is all about CNN.
Coming to the deep learning in the field of ophthalmology, basically deep learning in ophthalmology is mainly for the image-based diagnostic systems. Deep learning systems have been trained to perform visual interpretation tasks such as assessing retinal fundus images as well as diagnosing various retinal diseases. Well, one of the major strengths of the DS models is their ability to identify important features for the diagnosis, even if those features were not explicitly supplied by the inputs. Like if we don't supply explicit inputs, even it can detect and it can use those features. This makes DL as extremely powerful for the ophthalmology. In DL, networks have been shown to outperform human experts in diagnosing certain retinal conditions, such as plus disease in retinopathy of prematurity. Even DL can be applied in a variety of ophthalmological imaging modalities, including some OCT, fundus photography, and other things. Next slide. Coming to the application of deep learning in ophthalmology, one of the significant applications is assessing of retinal fundal images and images of high quality of suitable, like which images are suitable for the clinical purposes, and other things where the significant impact is like in the diagnosis of various retinal diseases, finding their like they are trained to recognize important features that are indicated for the specific conditions and all. Even they can be applied to multiple imaging modalities, including optical coherence and tomography, like which allows the ophthalmologist to use variety of imaging techniques to make informed diagnosis. And in this way, there are many applications of deep learning in the field of ophthalmology. Next slide. Now, comparison between the machine learning and deep learning in the field of ophthalmology, like machine learning mainly relies on the statistical models to learn patterns in the data and make predictions, while deep learning uses artificial neural networks with multiple layers to learn the complex patterns in the data. Next, machine learning has been used in the ophthalmology to diagnose retinal diseases using features extracted from the fundus photographs or the OCT images, while deep learning has shown like promise in the diagnosis as a range of the retinal diseases, which includes the AMD, diabetic retinopathy, as well as glaucoma. And machine learning algorithms typically require crafted feature engineering, like it is time consuming and may not capture all relevant information, while deep learning algorithms are capable of automatic feature extraction. Can save some time and money as well. And the deep learning can handle high dimensional data in this way. Like deep learning has shown more promising in the recent years than the machine learning, like as it can handle high dimensional data and automatically extract features. Next slide. Coming to the challenges, like deep learning has great promise in ophthalmology, but it has some limitations as well. One of the challenges is like the quantity and quality of the data. Like it can be especially challenging when developing models for identification of rare diseases as well, where datasets may not be readily available, and datasets are not always accurately labeled by human graders, so there is always an error in that performance. As well as one of the major drawbacks of the deep learning is the black box problem. Like it is not exactly clear where features are identified or how they are informed the model output and etc. Next slide. Coming to the conclusion, like artificial intelligence has shown tremendous potential in the field of medicine, particularly for developing advanced diagnostics and predictive tools. As we look to the future, like it is possible that AI-based programs may become a key component in the patient's clinical visits as well. And to fully realize the benefits of the AI in the medicine, it is essential that the physicians can take an active approach to understand the theory and applications of this powerful technology. And the goal of understanding AI in the medicine is like to provide the best possible care for the patients by using the innovative technology and the work collaboratively to develop new AI-based tools and solutions. We can unlock new possibilities in healthcare and create a better future. Thank you.